Here is Warren Howard, and he's going to talk about constraining the exoplanet atmosphere with multi-length flare campaigns. Take it away.
Well, first, I'd like to thank the organizers for having me and all of you for listening to me drone on for a few minutes. I'm excited to talk with you about characterizing exoplanet atmospheres with multi-wavelength flare campaigns. So first, JWST is beginning to characterize the atmospheres of terrestrial exoplanets and not just larger planets, or at least their secondary atmospheres, for the first time. And these terrestrial planets largely orbit M-dwarf host stars due to various signal-to-noise constraints. However, M-dwarfs are also known for their high levels of stellar activity, which can impact both the characterization and habitability of these small planets. Why? First, the largest stellar flares increase the brightness of the star by factors of 100 times in the optical, which ultimately can be associated with FUV and X-ray flux that drives disequilibrium chemistry in terrestrial atmospheres. And one such flare I'll show here on the left from Proxima Centauri, which hosts the nearest potentially habitable exoplanet, Proxima b. So you can imagine if you're standing on the star and looking, or standing on the planet looking up at your star getting 100 times brighter in the span of a few minutes, that would have some impacts. Next, the smallest flares contaminate transmission spectra, and we'll talk more about that in the second half of the talk, but this can potentially induce false positives in your exoplanet atmospheric retrievals. And an example of one of these contaminating flares is shown for TRAPPIST-1b here. The flare is highlighted in gray, and you can see how it's changing the expected shape of the transit. My research explores the multi-wavelength emission of stellar flares and their impact on exoplanet habitability and characterization in two ways. First, by carrying out the first population-level survey of M-dwarf flare stars with ALMA, Chandra, Swift, and TESS, and then second, using flare spectroscopy to determine the challenges that stellar activity creates for transmission spectroscopy. We'll start with the first of these. First, though, what is a solar or stellar flare? Flares occur when magnetic reconnection events in the corona accelerate charged particles down magnetic field lines towards the surface of the star, which heats the plasma. And this results in a fast rise exponential decay light curve profile lasting sometimes seconds to sometimes hours, and they generally follow a light curve shape similar to this. No one observation or wavelength can give us a complete picture of the physics at work or the wavelengths during a stellar flare. And to see why, look at the two figures below, starting with the one on the left. The point of this figure isn't to walk through every possible emission mechanism in a flare, but to point out that different physical processes in the flare emit at different wavelengths and at different times. And just to give one graphical illustration of that, this is an AIA image of a solar flare in different wavelengths in the UV, and the flare looks almost completely different in each of these different wavelengths. So clearly, we need multi-wavelength observations to be able to really understand all of the processes at work in stellar flares. The detection of the first millimeter flare from another star, Proxima Centauri, ultimately led to a simultaneous 40-hour multi-wavelength campaign from X-ray to millimeter wavelengths. And I show each of the contributing observatories and wavelengths below, all the way from ALMA and the millimeter to Chandra and the X-ray. And I wish I had time to talk about all of the amazing science that's being done coming out of this campaign, but I only have 12 minutes, so I'll just show one result from this. Here we go. And that's a large flare from Proxima Cen that we observed on May 1st, 2019 with ALMA in the top panel, TESS in the middle panel, and then HST and the UV in the third panel. And the thing that was most intriguing about this event is that the millimeter emission and the UV emission were in perfect lockstep, while the optical emission was weaker and a bit delayed relative to the other two band passes. And this is important because the UV is directly relevant to photochemistry and exoplanet atmospheres. And this raises the question, could the millimeter observations be a way of potentially tracing the high energy radiation environments of exoplanets from the ground? However, we need more than one star to know if this is actually true, or if this just happens to be something that's unique to this particular flare on this particular star. To answer this question, I'm now leading a simultaneous campaign at X-ray, near UV, and optical wavelengths for the first population of ALMA flares from 7 M-dwarfs of various ages and activity levels. And I illustrate those 7 M-dwarfs with yellow boxes here. And you can see that these are indeed many of the nearest and brightest M-dwarf stars on the sky. And I want to also show this data in a table format just to really bring home the different spectral types and distances and ages and wavelength coverages that we have for each of these stars. And again, I wish I could talk about all of the amazing science that we're going to do across all of this data, but for the sake of time, I'll just illustrate one of these things. And I feel that it's only appropriate to highlight the Chandra data since we're being hosted this week by the Chandra X-ray Center. So we obtained simultaneous Chandra observations along with our ALMA observations of 2 of our stars, and that's Wolf 359 shown on the top, and then on the bottom is Proxima Cen, and we highlight times during flares with gray panels. And this is interesting because Wolf 359 is a young analog of Proxima Cen, which allows us to explore the evolution of the high energy radiation across planetary evolutionary timescales. And that is in turn important because the high energy radiation directly impacts the atmospheres of rocky exoplanets. And in fact, many of these exoplanets exist in a photochemically dominant regime where their atmospheres are very, very sensitive to the amount of radiation at these wavelengths. And I'll give an example of that for TRAPPIST-1e. So this is a steam atmosphere model of TRAPPIST-1e, and we show different amounts of ozone production for different sizes of input flares. And as you can see, changing the size of the flare and therefore changing the amount of ozone significantly changes the observed transit spectrum. This is also a great segue to the second part of the talk, which is talking about the challenges that stellar activity create for transmission spectroscopy of rocky exoplanets. So perhaps the best system to help answer the questions of how stellar activity impacts rocky exoplanets is the TRAPPIST-1 system, which is a nearby ultra-cool dwarf with 7 terrestrial planets, 3 of which orbit in the habitable zone. And I show a brief schematic of these planets at the top of this slide. And these planets have orbital periods of about 1.5 to 18 days, all orbit extremely close to their host stars, and have masses and radii roughly comparable to Mars-sized to Earth-sized planets. Many JWST programs are observing TRAPPIST-1, including the NEAT collaboration, which is the data that I'll be presenting during this talk. So TRAPPIST-1 stellar activity does not make transit spectroscopy easy. The star has star spots, plages, stellar flares, coronal mass ejections, microflares, faculae. I could keep going, but I think you get the picture. So why does any of this matter for transit spectroscopy? The answer lies in something called the transit light source effect. So the path that a planet takes across its star when it transits is called the transit chord. And by comparing the spectrum of the transit chord with the pre-transit spectrum, which is shown in blue on the top, we can then identify what changed, which should be the planet spectrum shown in green on the bottom. But what happens if the spectrum of the transit chord differs in some way from the spectrum of the rest of the star? Say, for example, that we occult a star spot. Now, the assumed light source is a little bit different from the actual light source. And as a result, the observed transit spectrum actually differs from the underlying true planetary spectrum. To summarize, any difference between the spectrum of the transit chord and the spectrum of the rest of the star causes contamination. And this can include occulted spots, unocculted spots, or time variability such as flares. And for the rest of this talk, we'll talk about time variability such as flares. Why? Because TRAPPIST-1 is an extremely active flare star. So far, flare contamination in our data has been observed in transit spectra of TRAPPIST-1b, D, F, and G. So maybe this star is slightly less ideal than we had initially thought in terms of exoplanet spectroscopy. I'll give an example of 2 of those here, TRAPPIST-1f on the top and then TRAPPIST-1b on the bottom. And then the top of these 2 plots, I show what the expected transit shape should have been using a Batman model, and then what the actual spectrum is when we observed the star and then took a wavelength integrated light curve. And if you subtract off the transit model, what you're left with, lo and behold, is a flare. And then we also had a smaller flare during the TRAPPIST-1b data, and there'll be a paper by a different member of the team with a press release coming out about that. So I will say no more here. Thank you. The good news is that we were able to, the JWST covers the H-alpha line. It extends all the way down to 0.6 microns. So I was able to extract the H-alpha time series across all of our observations to identify when large flares might occur so that we could better understand their spectra across the near IR. So we observed 4 large flares, which would be roughly equivalent to X-class flares from the sun during this window. And I'll highlight those here. Again, you can see that fast rise exponential decay profile, and some of these are complex events. And to illustrate how we can go from the H-alpha light curve to the spectrum in the near IR, I'll use the case of flare 3 here. We can take the spectrum outside of the flare shown in gray and the spectrum during the flare shown in red, subtract them and identify a flare-only spectrum. And so we want to use these flare-only spectra to understand the effect that the flares have in the near IR. So let's discuss some results with our last few minutes. The first thing we find is the first characterization of flare continuum beyond 1 micron for any stellar flare. And so I'll show the peak spectra in the continuum for the 4 flares here. And we can see that these flares exist in the extreme Rayleigh Jeans tail. And so we can fit them with a black body with a temperature of around 5,000 Kelvin. And this is actually somewhat expected from the red optical with like 2 component flare models. So that's good. And the spectrum seems to do a pretty good job of fitting it, even with a model this simple. We're working on more complex models. You can see the near spec data on the top and the nearest data on the bottom. And in addition to the continuum, we also detected a number of lines, which I'll show briefly, but will not discuss in detail, except to say that these are the first detections of these lines in a stellar flare. So we now have line emission and continuum emission, so we can characterize flare contamination. We see at the blue end, we have about 20,000 parts per million contamination, and at the red end, around 2,000 to 3,000 parts per million. So can we use the nearest flare spectrum to identify and mask out lines, and then fit and remove the flare continuum in a consistent way that then allows us to recover the transits? This is the result when we do that. We have here transit spectra in wavelength bands across the range of nearest, from 0.6 at the blue end to 2.8 at the red end. And I've color coded these spectra with blue being the blue end and red being the red end. And the uncorrected spectra are shown for reference in gray for each of these bends. And we show the results before correcting for the flares using the method I just described, and then after correcting for the flares. And we see a significant amount of improvement, which is good. And again, this is a first order correction, so we're working on still improving this. But even with this first order correction, up to 80% of the flare contamination can be removed, especially from around 1 to 2.4 microns. So I'd like to wrap up by asking, is TRAPPIST 101 a wonder, or might this technique be more broadly applicable? GWST is also observing other planets around flare stars, such as AU-McB, L9859, and LTT1445A, not to mention others. So does flare mitigation have broader applicability? I would like to say that the answer is likely yes. And with that, I'll leave out my takeaways and thank you for your time.
Hi, I'm question about your flare related concept. Am I correct in inferring that your 2-minute delay is seen only as a result of test photometry?
Well, actually, no, it's not. It falls fully in the epoch after the peak that it would have occurred in from the HST data. So if I was able to zoom this data in and show that the x-axis error bars, it falls fully outside of the integration that would contain the millimeter and UV emission. So it's a real delay.
Okay. Is it consistent between test and UV, like the delay?
No, the UV also occurs in the integration prior.
Okay. We should talk about the test itself, because there are some timely systematic tests, 2-minute cadence that are not very well described to public by meditation.
That would be really helpful.
I think for the great talk. So when we're dealing with unocculted spots, we can, yeah, as we saw in the diagram there, you can get like a slope added, a negative slope, you can get like ghost absorption features of what you think is water, for example. What kind of spectral features could be printed into a transmission spectrum if you don't account for flares? Yeah, like that's unocculted spots.
Okay, for spots.
Yeah, so if you don't account for flares, what kind of signatures might you see in a transmission spectrum?
You're going to see a lot of weird like slopes in the spectrum, and there will be some features within those flare spectra that might, for example, look like the imprint of like water lines or something like that. And I would point out like some work being done by Laura Flagg on that point.
I want to know about your last point about the planets that are going to be concerned. I just wanted to know if it's just, do you have any insights on how do we know that AU-Meek and LTT are going to recycle 3 and cycle 4 targets? Do you have any insights?
I don't know. I'm just saying they're likely going to be targets because they have high signal to noise. They're nearby. There are a very limited number of such planets. And I know at least a couple of people who are writing proposals for at least a couple of these, myself being one of them.
Okay,
So
it's gonna happen.
I don't know. It might not be selected, but if it's not, then there's another cycle and another cycle and another cycle, and there's only a handful of these planets. So I assume that they'll be observed. Some of them though have already been heavily observed, and I list programs that have already done that.
Cool, thank you.
Hi, thanks for the really cool talk. So you mentioned, simultaneous multi-wavelength observations of stellar flares. And we're seeing these CMB surveys detecting a lot of these flares in the millimeter. And I'm wondering if there's any time scale for alerts that would be useful, or if it's, at that point, it's really too late to repoint your telescopes.
Time alerts are great. Right now, most of the multi-wavelength events have been captured just by chance using tests and like say the South Pole Telescope 3G or things like that. I actually had some slides on that, and as I was whittling this down to 12 minutes, I threw those out. But yes, alerts could be helpful for like rapid slew follow-up, and there are facilities in the optical that could do that.
Okay, cool. So alerts on like tens of minutes would be useful, or?
Potentially for the very largest flares, but those are the ones that are going to be the strongest foregrounds, so probably yes.
Okay, cool, thanks.
Okay, let's swing forward again.
Why would you hear you?
Okay, so our next speaker is Jessica Fett, and she's going to talk about tales of escaping exoplanet atmospheres.
Thank you. Hello, I just started my fellowship on September 1st. Very excited to begin this new chapter. Thank you so much for having me. I'm going to talk a bit about what I'm planning on doing, or the theme of what I'm planning on doing for the next 3 years. And it really focuses on the tales of escaping atmospheres of transiting exoplanets. And this talk is basically why I'm really into tales. So why should we care about atmospheric escape? This is an artist's impression of the approximately 20 Earth-sized planets that are in the habitable zone of their host stars. And so all of these planets, except for one, orbit M-dwarf stars. Now, this may be a problem for the question of habitability because M stars are pretty violent. So this is just an image of a video of the sun. And you can't actually see the Earth. The Earth is a tiny blue dot up there, which is so small that you can't even see it. It's right next to a CMB event. Also, I'd like to draw your attention to the area around the sun that you can see. This fairly constant halo of material streaming out is the solar wind. I'm really interested in the solar wind and also the winds of other stars too. Now, it's actually very difficult to measure the winds of other stars besides our sun. So far, we've only actually had about 20 measurements of these things. And the way you do that is you look for the interaction with the edge of the stellar wind with the ISM, and you can sometimes see emission at Lyman alpha wavelengths. And so this is how we've managed to measure the strength of stellar wind for about 20 stars. And this is a plot of the strength of the stellar wind inferred from those measurements with the X-ray flux, which is a measure of the activity of these stars. So we think that with increasing stellar activity, the strength of the stellar wind seems to increase as well until a certain point. When you reach these highly active stars, this linear trend you see kind of disappears and it becomes a hot mess. So for these very active stars, M-dwarf stars, a lot of those are very active, it's actually very difficult to predict the strength of the stellar wind. Now, a stellar wind can strip away a planetary atmosphere, but we actually don't know how strong these stellar winds are, and we don't actually understand how all these stellar winds can strip atmospheres away. So this is a question for habitability, this atmospheric escape. Also, when we look at the population of known planets, we can see that there are signs that photoevaporation, atmospheric escape, has sculpted them. So these are all of the planets closer than about 0.1 AU. The planets at the top are easy to find. These are the Jupiter-sized planets, and the planets at the bottom are much more harder to find. They're these smaller planets. And there's a gap in between Jupiter and Neptune-sized planets at very close in distances. This is called the hot Neptune desert. Planets here should be very easy to detect, but we see a large gap here. Why is this? We think it's maybe the planets that are born here have their atmospheres stripped away. So this is a large-scale effect of atmospheric escape that is sculpted in the bulk population of planets that we see. And it's very difficult to understand the population of planets that we have if we don't understand how atmospheric escape works. How do we study atmospheric escape? This is an image of the Earth at broadband UV wavelength. And so there's a large halo of material, this is hydrogen, surrounding the Earth. So this is emitting actually at Lyman alpha wavelengths. And so the upper atmosphere of the Earth is very extended up to about 7,000 kilometers above the surface of the Earth. And it's slowly trickling away into space about 90 tons per second. There are 5 quadrillion tons left in the Earth's atmosphere, so we shouldn't worry too much. But it's strong absorption lines of very abundant species in the upper atmospheres of exoplanets that are really important for studying atmospheric escape. This is essentially the method that we have been using for about 20 years to study atmospheric escape for exoplanets. We look in this UV line, Lyman alpha line, and see extended atmospheres around exoplanets and infer their escape rates. And this happened for the first time in 2003. The first ever transiting exoplanet to be discovered, HD 209, a couple years later, was also observed at Lyman alpha wavelength with HST. And so the white light curve model is what we expect the size of the planet to be in optical, and the brown and white data points are what we saw in Lyman alpha. So the planet looks about 10% the size of the star at Lyman alpha. So this suggests there's a huge cloud of material surrounding and escaping from this exoplanet. Another very famous Lyman alpha observation came quite a few years later. This was the most dramatic example of atmospheric escape measured in the Lyman alpha line, GJ 4360, a warm Neptune. You can see that the dip in the light curve starts a couple of hours before the fiducial transit. So that's when we expect the planet to transit, those vertical dotted lines here. And the absorption extends many, many hours post-transit as well. So what this means is that there is an absolutely massive cloud of material that's forming this cometary-like tail surrounding the planet. And that's why the absorption extends so many hours after the transit, because there's a lot of material trailing behind. So these observations, these Lyman alpha observations, since the first one, HD 209, there have only been about 5 detections of this in the 20 years that we've been doing this kind of work. Part of the problem is that you can only observe Lyman alpha exoplanet transits with HST, and you can only do it for very nearby systems because Lyman alpha is absorbed by the IXM. One of the other problems that we've also faced is that we can only observe the absorption in the blue shifted wings of the line. And this means that this material that we're observing has been accelerated up to 100 kilometers per second and is streaming towards us. Now, exactly how that material gets accelerated so fast has been a bit of a mystery. And also there have been many systems where we expect to see very deep Lyman alpha transits in atmospheres that are very prone to atmospheric escape. We observe them and we actually see nothing at all. We see no Lyman alpha transits. Oh, this is an actual plot of the Lyman alpha line for GJ 4360. So that blue shifted part of the wing that I was talking about is shown there on the left. And this is where you can see an absolutely massive drop. So the stellar Lyman alpha line is shown in white. And the blue line is what we observe when the planet is in front of the star. And you can see an absolutely massive drop in the flux at those blue shifted wavelengths up to 100 kilometers per second. When I was a grad student, we made the first observation of helium in an exoplanet atmosphere. And this was around the warm, inflated Neptune mass planet, WOS 107b. This is my favorite exoplanetary system. This isn't the data that we saw originally. Came from a few years later, and we re-observed the planet with Keck at high resolution. But we see in the light curve of WASP 107b, this material trailing behind the planet for up to 80 minutes after the end of the transit, which happens at those gray dotted lines here. I'm really happy to be here in Boston, because between the discovery and the publication of the paper, I came to the CFA and accidentally met Antonia Klopcic, and she is a theorist who is predicting that we should be able to detect helium in the atmospheres of these exoplanets. And it was a total chance meeting, and like she showed me her theory, and she like had these predictions that we should be looking for helium in the atmospheres of escaping atmospheres of exoplanets. And I had the observations, and I was like, oh, we found it. And we had this like amazing moment where like both of our heads exploded, and now we're good friends and we collaborate a lot. But anyway, since we made this detection, we found I think 13 or 14 observations of helium in escaping exoplanet atmospheres, many of which have post-transit tails. So I think this is a new way that we can I'm very excited about what we can do with these helium observations. However, a lot of the models that we have in an attempt to predict the actual mass loss rates from these exoplanets have struggled. Many of our models predict very different orders of magnitude mass loss rates, even when we have these observations of helium. This is one beautiful model, a 3D numerical model from Wang and Dai a few years ago. This is for the WASP 107 data. And you can see the density of the helium in the colored plots here. In this model, they actually included stellar wind effects, one of the first times. So stellar wind is one of the things that many people don't include in their atmospheric models, and we're actually still not sure how important it is for atmospheric escape. But we think the stellar wind is actually what is sculpting this escaping material into the streaming tails behind. I'd also want to highlight this incredible work earlier this year led by ZJ. This was the largest tail of any exoplanet that's ever been seen, with this helium line extending 50 times the size of the exoplanet and seemingly being sculpted by stellar wind. But also in the end of this paper, they kind of highlighted one of the difficulties of doing this helium work. So these are all of the helium detections that have been made so far in 4 different plots. So the size of the transit depth is on the y-axis, and the x-axis shows different properties of the system, the incident XUV flux, the surface gravity of the planet, and there seems to be no obvious trends so far in the transit depths of these systems. So we're still struggling to be able to predict for an individual system, what is the mass loss rate for these planets? What is the size of the helium depth? We have a bunch of data now, but we haven't really managed to fit it into a coherent picture. And one of the reasons I'm really interested in the stellar wind is because I think it's a very important missing piece of the puzzle. As I've shown before, we don't have very many measurements of the stellar wind, but I think using the helium measurements itself can help us measure the strength of stellar winds and then include them in our models, and then back out just how important they are for atmospheric escape. This is a really nice work by John McCann, where they did 3D simulations of escaping exoplanet atmospheres, including the strength of stellar winds. And they find that when you increase the strength of the stellar wind, it sculpts the material into these narrower and narrower tails streaming behind the planet. And we can see this happening at high resolution with these helium observations. So this is a plot of the individual absorption spectra over time, starting at the bottom and moving up through the top. The start and the ends of the transits are indicated by the horizontal black lines. And we can map the radial velocity of the helium absorption over time. You can see that it does not exactly trace the radial velocity, the expected radial velocity of the planet. Instead, there's this kind of lip towards the top that streams blueward. And this, we think, is the material being accelerated by the stellar wind between the start and the end of the transit. So if we have the radial acceleration of the material, we can actually back out the strength of the stellar winds. And this is what Wang and Dai have done with their models. That's how they were able to get those beautiful 3D models of the streaming material. And for WASP 107, they're able to make an estimate of the strength of this stellar wind is about 10 times as strong as the sun, as our solar wind. So I think this is a way that we can add to that number of stellar wind measurements. Another thing that I'm really excited to do with tails is going back to the Lyman alpha. Going back to Lyman alpha. This was a neat paper led by James Owen last year. They suggest that what we should be more interested in is not the size of the transit depths for Lyman alpha, which have been very hard to predict. Some of them are there, some of them aren't there. Actually, what we should be focusing more on is the length of the post-transit tails. So they found that actually the size of the transit depth is actually set by the tidal forces more than the atmospheric escape rate. But what you can actually get from the length of the tail is how far can a neutral hydrogen atom travel from the planet along the planet's orbit until it gets ionized and you're no longer able to observe it. So the length of the tail gives you that distance, and from that you can back out the velocity at which the planet has, the material has left the planet. We have some transit measurement of HE 18945E, which I'll leave up there and take any questions.
Next time. Quick questions, because I want you to have questions.
Yeah.
Would you talk about it? What is this plot showing?
We re-observed HE 209 in Lyman alpha, and we do see a post-transit tail. And so we're going to try and use that to get a better estimate of the mass loss rate from this planet.
What does it mean for a planet to be losing that much atmosphere? For example, for 107, what's it into its chemistry and perhaps?
Yeah, for WASP 107, not much probably. The rate that it's losing its atmosphere is, I think it's losing like 1/10 of a Jupiter mass every 10 gig years. So it's not going to have a great effect on WASP 107. I'm hoping we can use these lessons learned to apply them to other planets which have more dramatic mass loss rates.
I was wondering how these techniques might apply to the mission, the Colorado ultraviolet transit experiment by Kevin France, which is doing 200 to 300 nanometer spectroscopy to look for these sorts of tells. And I was wondering if maybe they could be looking for helium too or something like that.
You're right. Yeah, I don't know there are any helium lines in that wavelength range, but there are other absorption lines. Yeah, didn't have time to talk about it, but the more lines we have for a single planet, the better. And we can actually try and get at the composition, how much of the heavy metals are being dragged up by the atmospheric by that. Yeah, so yeah, that would be very good.
Thank you. Let's thank Jessica again.